Good morning, friends. I've just come back to this page, Principles of Nature by a gentleman named Wayne Roberts. I finally enabled the flash in the browser so it could play this tiny movie where he pronounces it as Utrigon, not Utrigon. I've been saying Utrigon in past videos. Now I'm going to try to change my habits and say Utrigon. One of the deficiencies of his definition is he doesn't deal with the corner case of what if all what if all three angles are 60 degrees? Is that still a U-trigon? And for our purposes, it would be helpful to include that corner case. He proves by a step-by-step theorem here, which is not the U-trigon theorem, the one that you'll see in Cut the Knot has the U-trigon theorem, as well as Mathematica Wolframsite. But this proof is more just that. The two lengths coming from the 60-degree angle, the ones that define that 60-degree angle, multiplied together give an area that can be expressed in terms of equal area units, or ETUs. And this becomes more fleshed out in synergetics. So here we've got this, you could say, is kind of what Wayne Roberts is interested in. Now, he's not, to my knowledge, from what I can figure out at his website, any kind of quote unquote disciple of Buckminster Fuller. I don't think so, right? It's not my impression. You can contradict or correct me if that's necessary. In any case, we've got 4 units up the side to the left and 3 units up the side to the right. You just do what I call close the lid, and you can prove that this area, the green area, is equal to 12 units, where a unit is an equilateral triangle, right? So what we do in the Fuller corpus and synergetics and what I'd call Martian math in order to better package and market for an imaginative audience. I'm kind of introducing science fiction, actually. And I introduce science fiction writers, in particular H.G. Wells, not just for War of the Worlds, but for his nonfiction writing between the two world wars. I don't mind a math that kind of comes with a specific history as well. And I'm no big super expert on between the wars, by the way. I'm catching up in my older age here by watching YouTubes and studying, and I'm still like full-time student. Never mind that I'm also a teacher. So as you can see, as I go through my Martian math storyboards here, I'm giving examples of where the U-trigon discovery that we get from this other site, Principles of Nature, that principle is being proved here by Wayne Roberts. Let me close some stuff here. Now here we are in REPL.it. Been here a few times in the YouTubes. I am, in this case, using the Fuller version of the theorem. You could say it was like going to a next higher dimension, where I'm going with, excuse me, gotta find my window here. Let's see, okay, where I'm going with this other view of the matter. A regular tetrahedron, all angles the same. Here again, I branch out 3 lengths from any corner and close the lid, but this time we're in what we'd conventionally call 3 dimensions. And it's the volume now that I can express in terms of any one of these unit tetrahedrons. We could call these edges units, and then this whole volume here would be 1, 2, 3, 4, 5 to the third power, right? So 5 times 5 times 5, 125 would be the volume of the entire tetrahedron. But inside here, we're just doing 2 times 2 times 5, and that's 4 times 5, which is 20. So the shaded the tetrahedron comprised of the the part inside the closed lid, you could say, that's a volume 20. We've got a very interesting volume formula that Gerald de Jong came up with on a train. He scribbled furiously, did the algebra, distilled it down, and now he's lost the original like scribblings where he managed to distill this. It was like a Ramanujan moment where he came up with this formula, which we use to input just the 6 edges of any tetrahedron, right? Regular or not. It just has to be like a legal tetrahedron. And with a bunch of multiplications and additions and a final second root at the end, we're able to pop up the volume of that tetrahedron, just given its edges. And you might say, well, we knew that. There has been formulas like this before. And I'm saying, yes, exactly. It's not a new idea to take the 6 edges as input. But this particular formula, notice there's no there's no big constant like 1 over 144. You'll find that some of these other versions, they have to have some kind of constant. But this one just spits out in natural tetra volumes, right? It just naturally comes out in the units of these tetrahedrons. And we need that unit in order to make sense of the entire concentric hierarchy. You can't really get anywhere in synergetics if you don't comprehend how we are computing volume for this tetrahedron inside what we call the volume 3 cube. How could you call that the volume 3 cube? If it has edges second root of 2, the volume would be second root of 2 to the third power, not 3. And it's actually the ratio between second root of 2 to the third power and 3 that we use as a conversion constant to go between what our synergetics volume for this cube is and what the XYZ volume for that cube also is. We have 2 different sort of conventions for measuring volume, thanks to this sort of U-trigon way of thinking about both triangles and tetrahedra. Here you see them side by side, right? And once you've made that transition to this alternative mensuration regimen or protocol, hey, you got whole number volumes now and smooth sailing into what I call and what Fuller calls either the cosmic hierarchy or the concentric hierarchy. It should remind you of Kepler's drawings, which were meant to conform to the planets. Here we're just purely Platonic, as in Plato. We're not trying to map to the planets or even atoms at this moment. We're just doing the math, right? Defining various fragments or dissection results, the S module, the A module, the B module, and computing from scratch various other volumes in connection with the jitterbug. Now, Kepler was also big into the rhombic dodecahedron, and that's what we call volume 6 once we've based ourselves in this new multiplication world, right? And that gives us the close packing inside of which the spheres of the CCP and or FCC appear. So this is like core to crystallography, is this homogeneous sphere packing. If you try to imagine balls floating in water of equal density, you'd say equidistant apart, as uniform as possible, what would you come up with? And you might think at first of just cubes with balls at the corners of cubes, kind of XYZ like. But think of how the body diagonals there are different from the face diagonals, which are still different from the edge. You've got those different lengths of the cube. Substitute that mental image with 12 balls around a ball. And you've got what's called the CCP, and you've got many more equidistant links between ball centers. In fact, any 2 tangent balls, and they are tangent now, if you make them big enough, they aren't in this picture, but if they do touch, then they, they each have 12 neighbors, and the distance to each of those neighbor centers is the same, and the distance around the circumference of this shape, the cuboctahedron, those distances are all the same. So we put a lot of emphasis on the cuboctahedron and the rhombic dodecahedron, which happen to be duals of one another, right, in synergetics. And we give one a volume of 6. These are relative to each other, and the relative cuboctahedron has volume 20. As I would hold up here, this would be volume 20. And we would put spheres at each of the corners and in the center. And we can condense this down, distill it down to the icosahedron and on down to the octahedron. And if we use the same edge lengths to define our unit volume, this would be our unit 1, our U-trigon equivalent, you could say. And this is geometry that is all American. In other words, Bucky Fuller was a New England transcendentalist, Bear Island, went to Harvard. So I'm going to wave the flag here and then say, hey, but did you ever learn any of this? And it's been like over 40 years that this stuff's been out there. Have you gotten it in school? Has anybody bothered to teach you any of this geometry? And if the answer is no, then Fuller's other writings also illuminate in their importance, because he argues that we have slowly and then with exponential speed privatized our government to where now we no longer have what you could call public schools, because if we did, they would share what you're seeing right here, right? Some of this history and literature. So we have a pretty interesting case to make to the world that we have an interesting geometry we're studying, and it's embedded in some humanities writing that's also worth taking in. And that's what I do on this channel, is I help connect those dots for you so that you can, going forward at least, see things a little differently. And Martian math is how I'm branding it. And I would say we do have public schools in some sense, because out here in Siberia, in cyberspace, here it is. This is the material that's available to you. So at no charge. Talk to you later.